Let's spend this section discussing checksums and their importance and how they may be applicable to you as you conduct transactions across the net and with your business counterparts. So we'll label this section checksums. Now, checksums are very important because they allow us to confirm that data we've received has not changed in transit due to perhaps man-in-the-middle attacks or other compromises. So features integrity check of content. Nowadays, we're ever connected to the internet, and as a consequence, we're moving data to and fro. So we upload, we download, we move content in and out of the net, to and fro, business partners, friends, and others alike. One of the simplest checks we can make on any content we receive is a checksum, and if it is represented, the content that is, as a file, it's even easier to confirm whether or not the file's integrity is intact. Checksums generate hashes against your data. A hash is a unique string that corresponds specifically to the bit arrangement of that data. So if you have a file, let's say, that includes a text, "this is a test," for example, there is a unique checksum that represents "this is a test." Now, there are multiple checksum types. So integrity check of content and multiple types. They include, but are not limited to, MD5, and we have enclosed MD5 with single quotes to indicate that that is the name of the command that is run within FreeBSD. On other distributions of Linux, for example, you'll find that it's MD5 sum, but it performs the same function. And MD5 is a 128-bit based checksum utility, which is strong. However, there's also SHA-1, which is stronger at 160 bits, and also SHA-256, which is even stronger at obviously 256 bits. On other platforms such as Linux, there's also SHA-512. You can get SHA-512 for FreeBSD, but it's not included by default. Checksums are installed by default, so there's no need to install anything else. The base installation will include this setup for you. So how do we confirm content? Well, let's go through some tasks that are of interest. 1, generate unique checksums. Now, one ideal way to carry this out is to generate text. It could be as simple as "this is a test" or "my name is Dean," and attempt to confirm the unique string on a remote system, of course simulating remote systems separated by the internet. So let's see what that all amounts to. So in our shell, we're currently logged in as the non-privileged user Unix CBT. You need not be a privileged user to use tools such as MD5. MD5 is in SBIN. SHA-1 is in SBIN. And SHA-256 is in SBIN. How do we know whether or not we can execute these items? Well, let's do an LSL, and now that you know a little bit about command substitution using backticks, which SHA-256. This sends the output of which SHA-256, which is simply /SBIN /SHA-256, into the input of LSL. Notice that it's executable by everyone. The last 3 bits represent everyone else, or other. The first 6 represent the owner and the group. So everyone can execute these programs. SHA-256, SHA-1, and MD5. So they're definitely available for everyone on the system. So how do we confirm content? Well, we start with the simplest of them, or the weakest of them, which is strong by most standards, but not as strong, of course, bitwise. So let's MD5. Now you execute MD5 with no options. It's waiting on standard in. Whenever a program returns a blinking cursor as you see here, it normally means it's waiting for you to supply data. Sometimes, however, the program could be performing some tasks in the background, such as reaching out to the net, or perhaps computationally intensive tasks, which causes it to tie up your console. In this case, MD5 is simply waiting for us to supply a string on standard in. Standard in defaults to receiving its information from the keyboard and alternately from a file. So let's go ahead and type in "this is a test," and we'll terminate it with a a period. Now notice, after pressing enter, we're allowed to type in some more text. When you've finished supplying the text that's of interest, execute Control-D. Control-D signals to the program that you are finished with the standard in stream, and that's usually the case for most programs. Now let's try this as a test, sans an extra line, by executing Control-D from this line. And let's compare and contrast. Notice that the strings that we see here are actually different. This is a test sans a new line differs from this is a test with a new line. So let's go ahead and note that MD5 executed by itself, and let's just note returns. So first of all, it waits on stdin for input, so you should use Control-D to terminate standard in stream, and then it generates a unique fingerprint representing the content. Now, how do we know that this string will play out on remote systems to communicate to the recipient that the data have not been compromised in any way? Well, the thing to do is pretend you're another user, connect to a remote system, and try the same test. So let's open a new window. We'll Control-Shift-N so that we can see it in both windows. From here, we'll SSH as a user Linux CBT to our remote system, 168.75.101. It's a Linux system running Debian, Linux CBT build 1. And momentarily it should come back, prompting us to accept the public key if we've yet to authenticate as this user Unix CBT, meaning the known underscore hosts file may not contain the entry. If it comes back, when it comes back, we should then tell it yes, and then we'll connect. And since it's taking a while, what we can do is send a few packets using ping. So let's send 3 packets to the host, 75.101, and it's not responding. That's why it hasn't come back. So let's boot that box up, and we can have this ping run without a counter. Eventually we'll see the packets returned. So that's why it's not coming back. So we'll keep these 2 windows going. So we have a unique string for this is a test sans a new line. Let's go ahead and copy that and paste into our notes in between single quotes. So there's a string. This is a test. Generates the following. So the key now is to confirm this string on another system using MD5. And if the string returns identically, then that tells us that the content has not been altered. That's the idea. So if you send content from your system to a remote system and the checksum passes, meaning the sent string is the received string, then the content has not been tampered with. It doesn't mean the content hasn't been viewed. Let's just note, checksums do not guarantee that a man in the middle has not viewed your content. It simply means that the content, so let's just note, it simply means the content is intact. In other words, its integrity has not been damaged. It has not been rearranged. None of the bits have been touched, which also implies that if you alter any of the bits by even a single character, for example, if you put a space between the I and the S, it changes the MD5 sum. Or if you change one of the characters, let's say the I here to the number 1, which is rather subtle, that would change the MD5 or SHA-256 string. So this is still waiting for that remote system. Let's go ahead and show you the differences on the other terminal. So MD5 waits for us, and let's go ahead and note this, and instead of I, we'll use the number 1, is a test, Control-D twice, and notice the string is different. It terminates with A3. The original string terminated with 19. Now you may be wondering, does the MD5 or checksum string vary with time? Well, let's do MD5 again. This is a test, same string. And notice that this string terminates with 0019 and it begins with 120. So no, the answer is it doesn't vary with time. So let's just note checksum strings do not vary with time, as do other protocols. They are solely content dependent. So it's really a question of whether or not the content has been altered, any that's of interest. Now let's see what's happening. Ping is throwing us a buffer error, so we'll let that sit out for a moment. All right, so now let's aggregate our strings. So this is a test MD5 sum, comes back with the string above. Now let's do the same on the SHA side. This gives the other system a little time to come up. So SHA1, same thing. That's going to generate the following. They all support, by the way, the same option. They're part of the same package. So this is a test. Control D twice. There's the unique 160-bit string, which represents this is a test. And also this begs the question, how do you transfer this information across the wire? You can simply email it or publish it on your website, as is the case with many vendors. So it generates this string. That's the 160-bit string. And SHA-256 will generate what we present momentarily. So SHA-256 tab completion. And here's an even longer string. So let's get this into our notes. So those are our three strings that we'd like to confirm on the remote system. Now, while we wait for the other system to come back up, if it comes back up, in the interim, we can continue to test, even from our local system. So from this window, for example, let's test using the three algorithms, the same string. So MD5, now instead of waiting on standard in, we can just use the S option, and in between quotes, specify the string. This is just like being on another system, and it's as simple as comparing and contrasting. So notice it starts with 120E, which the other string reflects, and terminates with 0019. Similarly, SHA-1 will return a string that terminates with AC88. That's the same here, and begins with AFA, which is the same here, and SHA-256, which is essentially the test that we would perform. So let's see, this terminates with 562C, and let's see this one here, 562C, so it's the same string. So the idea is that regardless of how you present the string, it'll come back. So for example, we can execute SHA-1, or let's begin in order of bit strength, or SHA-1 or SHA-256, followed by the S option, followed by the string. This generates unique string or unique fingerprint for string. Now we're not relegated to strings alone. More ideally, we will generate these unique hashes against files, because oftentimes we download content from the net and checksums are provided. So the idea is that we'd like to be able to generate these strings against files. So generate unique checksums against files. So let's see what's of interest and how we can get one dump into one place. Let's see, for example, here is a tar file that might be of interest. Let's take this file, and we can generate strings against them. So using MD5, for example, let's just show you how it works. For one file, it's MD5 followed by the name of the file. MD5 reads the file name and takes in the content and generates a unique string and places it there. You can then send the output into a checksum file. So for example, MD5 against the file. We could even define the file name as, let's say, temp file or some variable name, and just reference that particular variable to save us time. So for example, we could say C file equals the name of the file followed by MD5 C file. And then if this works, we reference it against SHA-1 and SHA-256. So let's try this out. And there's a string. So that now means we can also use logical ANDing to do SHA-1 against C file. C file, I'm using C as a prefix to represent current, and it's customary to name your variables using uppercase characters in the bash shell. So SHA-1 C file followed by a SHA-256 C file. And this should dump all 3 strings. Let's reset the buffer. Reset is a way of resetting your buffer within the GNOME environment, and let's go ahead and generate those 3 strings. Now this generated the 3 strings to the screen to stand it out, not to a file. So to place this in a file, you could simply use a pen redirection at each step of the way, and that would create the appropriate file for you. So those are the 3 strings that are associated with this particular file, which can be confirmed on remote systems and is unique to those files. Now, if you vary the file by a single bit, it changes. So let's find a file that contains the text. It's the same thing that we've shown you with the text string that we've provided so far. So let's see if we've got some textual data. Let's take a look at temp. That's messages, temp2, 10 million.txt. Well, then let's create a simple file. We'll generate this as simply, we can do gedit to create the file. Or in fact, we could even use the notes file. But rather than corrupting this file, let's create a new buffer. And we'll just put testing. So this will be simply testing.txt. So now, if we generate a string, a file against this, C file will now be testing. And let's take a look. Let's ensure that testing.txt, that is. So we're missing the suffix. So testing.txt. And we should be able to place that in here. And now there we see the strings. Now let's vary it. So that's what we got the first iteration. Now let's just put a new line, which is not so noticeable. And let's go ahead and try it again. Notice it dramatically varied the produced fingerprints for all of the algorithms. A simple new line character did that. Now let's reset the new line and try it again. Now we're back to the original. Again, checksums are concerned not with time, but with content. So we varied the file over time, but so long as the content is reset to the original, then it works. So the key is when you generate these checksums, it's to publish somehow in a safe manner these strings. You could email or put it on a website, somewhere that you are the publisher and it's assured that you've supplied those strings. And then the recipient can confirm whether or not the content has changed any. So when you find content online, invariably, from a trusted source, of course, you'll find checksums for files that you download, ISO images, tar.gz, and the like. And it's these checksums that tell you whether or not, during transit, the file has changed. Now, of course, if someone hijacks the website of your trusted source, your quote-unquote trusted source, then they could also hijack the string. So let's just note, checksums are only as good as the security behind the provider of the content. So this really means if content provider's site/content is compromised, then the checksums will also, in all likelihood, be compromised. And then, or in which case, you cannot trust the checksums that you're checking against. And that's really the key. So we use MD5, SHA-1, SHA-256 against content that exists. It could be any sort of content, usually files or content provided on standard in. We can use redirection to place the content. So let's just spice this up a little bit. So we'll take this generation here, and as an alternate execution, we will place. So now we're generating the checksums MD5, SHA-1, and SHA-256, but we're not placing them in a file. So using append redirection, after each we could simply append, and here's where a variable can help us as well. So you can use the file name .checksums. That's a common way of distributing checksums. So into cfile.sums, for example, or checksums is one way of doing it. So let's just note that this needs to be to the right of here, and we'll just take this. Now the reason why we're using append redirection is to ensure that the file is grown as opposed to clobbered, because clobber will simply overwrite each time, saving only the last data. So let's include this into the mix, and then for the final incarnation for SHA-256, we'll place it once more, and this will generate the 3 sums that are necessary into an output file, and then we can deliver both files to the recipient, perhaps published via a trusted source such as a website for which we have exclusive secure control over, or via email. Or out of band, you can read the checksums to the person. So now let's go ahead and execute this, and let's echo the exit status to see what's transpired. We should now have a checksums file. So this is the source file, the daily backup file, which is 50,393 bytes, and its accompanying sums file is 272 bytes. Let's cat the sums file, and there we see the content represented per file. So each file for each algorithm, and then we can share these 2 files. Now insofar as clobber redirection is concerned, let's just show you what would happen if we employed that method. You'll see momentarily that the last item will be written, which is not the intended MO. So append, or that's output. We've changed append to output. This will be append to output, and the final one ditto. And then let's execute this, and you'll see what results in the final file. So let's echo the exit status. It's all clean, it looks good. And let's ls, and that's ls. And now notice, instead of 272 bytes, which we had before, it's 111 bytes, which obviously tells us there's a problem. Now let's recat the contents of the sums file, and you'll see momentarily it contains just the last item. Why? Because the initial file was written with an MD5 checksum using clobber redirection, so it was there for that instance. But as far as the shell is concerned, as soon as MD5 was finished with its process successfully, the shell invoked SHA-1 with also clobber redirection. So it truncated the file and wrote a new checksum. And when this portion of the process was completed, then the shell executed SHA-256 again with clobber redirection, which is why the final item is there. And that's why you need to use append redirection. So this uses clobber redirection to generate the checksum file, which preserves the final, in this case, SHA-256 checksum run. Whereas this item, this uses append redirection to generate the checksum file, which preserves all checksums in the process. Simple way, simple one-liner, but it preserves the checksums accordingly. And now you can share. So at this point, let's just note, armed with source file and checksum file, you may share both with recipient via a trusted source, i.e. website. And in that way, they can confirm whether or not the content has changed. And again, let's just also note, if you vary the content by a single bit, the checksums will change. possibly considerably. So keep that in mind. So the checksums are a very good way of ensuring that content is intact, the integrity is intact. If you need stronger than SHA-256, search for SHA-512. SHA is considered to be the best hashing mechanism, the fastest and most optimized hashing mechanism available today. MD5 is maintained for legacy purposes and is still considered to be strong, but not as strong as the available SHA algorithms. So that's a little bit about checksums and how they're implemented within our NIC's environment. Once our system's up, we'll transfer these files across the wire and confirm on the other system that the checksums are intact.